So let's look at a linear regression example to go over some of the things that we just covered at the previous video. So the data that we're looking at are home sales from August 2019 for the zip code 32807. Our explanatory variable is the heated square feet of the home. Now when I say heated square feet, we're not including the garage space, we're not including any patio space, just the actual living space of the home. That's our explanatory or our X variable. The response variable is the sale price in thousands. So for example, if a home sold for $89,000, that's going to be represented with a Y equal to 89. So that's our response variable. So this slide shows the scatter plot of our data. So if we look at the x-axis, that's our heated square feet. And if we look at the y-axis, that's our price in thousands. So if we look at this, we can see that we do have a positive relationship. Right? It looks like as the heated square feet increase, the price in thousands also increases. Now it's not a very tight pattern, there's some scatter there, but you can still see that there's a positive association between the two variables. So in this slide, we're going to work through coming up with what is the linear regression model. So I have some summary data up here at the top. I have the R squared. I have our heated square feet, the mean, and the standard deviation. Once again, that's our explanatory variable or our X variable. I also have the mean and the standard deviation of our sale price, that is the response or the Y variable. So we know that our generic format is our y hat equals b naught plus b1 times x, where the b naught represents the y-intercept and the b1 represents the slope. So first let's calculate the slope. Well, the formula for our slope is r times the standard deviation of the y variable divided by the standard deviation of the x variable. So I can get my 0.614, that's my r variable. The mean of my y, or the standard deviation of my y is the 52.91, and the standard deviation of my x variable is the 316.64. So I solve for b1, and that gives me a slope of 0.103. Now let's solve for the y-intercept. So my b naught is equal to the mean of my y's minus my slope times the mean of my x's. So once again, I just go back up to my summary data at the top there, and the mean for my y's is 189.53 minus my slope times the mean for my x's, 1,322.32. I solve for my y-intercept, and I get 53.33. Now I can take those numbers and just fill them into my generic equation that I have at the top, which gives me y hat equals 53.33 plus 0.103 times x. So now I have my linear regression equation. So on this slide, we have the residual plot. And my vertical axis represents my residuals, and my horizontal axis represents my heated area, which is my explanatory variable. Now if we look at this, remember we had talked about, in order for data set to be a candidate for linear regression, we wanted to see a random scattering on our residual plot. So if we look at this, there's no patterns that jump out at us. We don't see any outliers, just a random scattering of points. So based off of this residual plot, it looks like we do have a good candidate for a linear regression model. So on this slide, we're going to look at interpreting our slope and our y-intercept. So at the top of the slide, I have our linear regression model there. Our y hat equals 53.33 plus 0.103x, where x is our heated square feet and y is our sale price in thousands. So if I'm going to interpret the slope, I'm going to say on average, as heated square footage increases by 1, the sale price will increase by $0.103 thousand, or $103. So each time I increase my X by 1 unit, I'm going to be increasing my predicted value on average by 0.103. Now, if I'm going to interpret the y-intercept, I'm going to say for a house of 0 heated square feet, the model predicts the price to be $53,330. So one thing I want to point out about interpreting the y-intercept, when you interpret it, it may or may not make sense. Okay, but all you're doing is you're saying this is what the model predicts when your x equals 0, because when x equals 0, that's when your line crosses the y-axis. So you can be interpreting it correctly, and it still may or may not make sense, because it may or may not make sense for your for your x to be 0. Like in this case, you wouldn't have a house with 0 square footage. Okay, that's not a house. So it really doesn't make sense, even though it is the proper interpretation. So let's look at our r squared. So remember, the r squared represents the variability explained by the model. So for our model, our r squared was equal to 0.377. So what that means is 37.7% of the variability in the price of the home is accounted for by the heated square footage of the home. So obviously there's some other things in there that affect the variability of the price of the home, but for our model, we're only looking at the heated square footage, and that explains, based off of our sample data, that explains 37.7% of the variability in the sales price of a home. So this slide shows the scatter plot of our data. So once again, we have the heated square feet on the horizontal axis and the price in thousands on the vertical axis. So this is the same scatter plot that I'd showed you earlier in this example. What I've done here is I overlaid our regression model. So we have the y hat equals the 0.103x plus 53.33. Okay, so we've got our slope in there, we've got our y-intercept in there. What I want you to notice is the regression line that we have in there only intersects one of the points. And I want to bring this up because some people get confused and they think that the best fit line should intersect the majority of the points. And that's simply not the case, because remember, your least squares line, you're trying to minimize all of the residuals. Okay, so it has to take all of those data points into account. So you could have a least squares regression line that doesn't touch any of the data points. It just happens to be the one that minimizes all the residuals. So don't get confused by thinking that your least squares line has to intersect points. It doesn't necessarily have to intersect any points. In this case, it intersects one point. You may have other cases where it will intersect 2 points or more. But don't get caught up in thinking that it has to intercept a majority of the points or even some of the points. Okay, so let's put our model to use. So here we have a home that is 1,700 square feet, and it sold for $229,900. Okay, that's actual data value. What's the predicted sale price using our model? So if we take our 1,700 and put it in for our X and then solve for our Y hat, we get that it is 228.43, or we could say that as $228,430. Okay, that's our predicted value. So what's the residual for that point? So remember, our residual is our actual or our observed minus the predicted. So our actual was 229.9. Our predicted was 228.43. So that gives us a residual of 1.47, or if we use it in dollars, we can say 1,470. Okay. So then the question is, did the model over or under predict? Well, as we had talked about before, the residual is positive. So in that case, the model under predicted the sales price of the home. Right? You've got a positive residual. The actual sale price of the home was $229,900. The predicted value was $228,430. Okay, so it underpredicted. The value that the model predicted was less than what the actual value is. So in that case, the model underpredicted the sales price of the home. Okay, let's look at another one. In this scenario, we had a house that had a square footage of 2,438, and it sold for $225,000. Okay, what is the predicted sale price using our model? So you take the 2,438, put that in the model for your X, and solve for your Y hat, and that gives you 304.44, or $304,440. So what is the residual? Well, if we take the 225 minus the 304.44, that gives us a negative 79.44, or a negative $79,440. Now the question, did the model over or under predict? Well, in this case, our residual is negative, so the model over predicted the sales price of the home. So if we look back at our data, okay, the home actually sold for $225,000. Our predicted value was $304,440, so that's an over prediction. That's what gives us the negative residual. So once again, the residual is negative, so the model over predicted the sales price of the home.